Hello friends, today I am going to discuss some of the important name reactions which we study in carbonyl compounds generally. The first one of them is Beckmann rearrangement. The first name reaction which I am going to discuss today is Beckmann rearrangement. Now what actually Beckmann rearrangement is? So this is acid catalyzed conversion. This is acid catalyzed conversion of ketoximes. I hope you have idea about ketoximes. So it is acid catalyzed conversion of ketoximes to N substituted amides. Right. So what actually ketoximes is? So when a ketone is treated with hydroxylamine, the product which we get, that is known as ketoxime. Let's write that reaction first. I'm directly writing the reaction that if I'm having a ketone and it is treated with hydroxylamine, which is NH2OH, so the product which is formed is RCR dash double bond N and OH. This compound which is obtained, this compound is known as ketoxime. And when this ketoxime is treated with H+, it rearranges itself to give you N substituted amide. Let's see that reaction if I'm having RCR dash double bond N and OH. And when this is treated with H+, the product which we'll get, that will be R dash C double bond O N H and R. So this product which you are getting, it is N substituted amide. Now point is that between R and R dash, which alkyl group is going to migrate, this how will we decide? So the alkyl group which is anti to this OH, the alkyl group which is anti to this OH, that alkyl group will migrate in this reaction. Let's try to understand the mechanism of this reaction first. Let's try to understand the mechanism. Initially we were having RC R dash double bond N and OH, and it is treated with H+. So what we know that oxygen, because of its lone pair, is electron rich species, and the H+ which are having, that is electron deficient species. And in chemical reactions, what happens? The electron rich species attacks on the electron deficient species. So oxygen is going to attack on this hydrogen. So if it is attacking, the product which is formed is RCR dash double bond N, and this part will be converted to OH2 positive charge. O is developing positive charge because it has donated a pair of electron to hydrogen or H+ ion. After this, what will happen? This alkyl group which is present on carbon, that will migrate to this nitrogen, and this group will depart in the form of H2O. So the product which will be formed, that will be R dash C with positive charge, double bond N and R. This alkyl group which is departing, that is departing in the form of R minus. Now after this, what happens? The water molecule that has departed from the substrate, that will be electron rich, and this electron rich will have a tendency to attack on electron deficient species, and the carbon which we're having in the compound is having a positive charge which indicates that it is electron deficient. So lone pair of oxygen will attack on this carbon. If it is attacking, the compound formed will be RCOH. O will develop again a positive charge because it has donated a pair of electron to the carbocation, then double bond N and R. After this, what we know, that positive charge on O is unstable, so this electron will migrate to oxygen, and this compound will be converted to R dash C OH double bond N and R. And what we know, that this compound is enol because OH, it is not exactly enol, it is a type of enol because OH is attached to sp2 hybridized carbon, and this compound will tautomerize. Tautomerization, I hope you have idea. Tautomerization, what happens? That hydrogen migrates from one atom to another atom. So this hydrogen which is present, that will migrate from this oxygen to nitrogen, and the compound which will be formed will be R dash C double bond O N H and R. So this product which we have obtained, this product is unsubstituted amides. So this rearrangement, entire rearrangement which is taking place in presence of H plus, that is known as Beckmann rearrangement. I hope this concept is clear. Let's do one basic question on this. So let's suppose we're having CH3, C, CH2, CH3, double bond N, and let us suppose OH is present over here, and this compound is treated with H plus. So this is ketoxime, and ketoxime is treated with H plus. So there will be Beckmann rearrangement, and this alkyl group is anti to this OH. So this alkyl group will migrate to nitrogen, and the product formed will be CH3, C double bond O, N, H, and will have CH2, CH3. So I have done a very basic example of Beckmann rearrangement. After completing all the reactions, I will give a worksheet on these reactions, rearrangements, and that will be discussed in later videos. The first reaction that we have completed is Beckmann rearrangement. The second reaction which we are going to discuss today is benzylic acid rearrangement. The second reaction which we are going to discuss today is benzylic acid rearrangement. Let us suppose we are having a compound like this: pH, C double bond O, C double bond O, and pH. And this compound in presence of NaOH is converted to pH, C, OH, pH, C double bond O, O minus, and Na plus. So this rearrangement of this compound, that is known as benzylic acid rearrangement. Now let's try to understand the mechanism of this reaction, mechanism of benzylic acid rearrangement. So first of all, we are having pH, C double bond O, C double bond O, and pH. And in presence of NaOH, in presence of OH minus, what will happen? OH minus is a nucleophile. So nucleophile will attack on carbonyl carbon. If it is attacking, the pi electron will shift to oxygen. In the second step, the pi electron will come back, and this pH minus will come out. And this pH minus which is coming out, that will again behave as a nucleophile, and that nucleophile will attack on the carbonyl carbon, and pi electron will be shifted to oxygen. So if I write the product will be, first we'll have pH, this pH which is connected to carbon, this carbon is having O minus, this pi electron has shifted to oxygen, so it will have O minus. pH will be attached to this carbon, then single bond, double bond O, and OH. Now what we can see, that this hydrogen which is present, that is acidic hydrogen, and this O minus which we are having, that will have basic nature. So that O minus will take over this acidic hydrogen, and the product which will be formed, it will look something like this: PHCOH, C double bond O, O minus, and this O minus will attract the Na plus which is present in the solution. So this is the mechanism of benzylic acid rearrangement. I am explaining again what is happening. First, in presence of OH minus, which is a nucleophile, OH minus will attack on the carbonyl carbon. First step, pi electron is shifting to oxygen, and after that the electron is coming back to its original position. I hope you remember SNAE mechanism, nucleophilic substitution by addition elimination. It is a type of that reaction, and pH is coming out in the form of leaving group, and that pH minus which is coming out, that will again behave as a nucleophile. So that nucleophile is attacking on another carbonyl carbon, and as it is attacking on carbonyl carbon, the pi electron is shifting to oxygen. So oxygen is developing a negative charge. So in the overall compound, we are having one oxygen which is having a negative charge, and other oxygen is having hydrogen, or we can say is having acidic hydrogen. So the basic oxygen which is O minus, that will take away the acidic hydrogen. So the compound which will be formed is this. So this entire reaction is known as benzylic acid rearrangement. Now let's do one question on this benzylic acid rearrangement. Let us suppose we are having this compound, one benzene ring with C double bond O, single bond C double bond O, and we are having benzene, and at para position we have OCH3, and this compound is treated with NaOH. Now in this, what should be our approach? So what we know, first point, that OH minus which is present, that is electron rich. If it is electron rich, that will try to attack at electron deficient position, and the electron deficient position in the substrate is our carbonyl carbon. So we have two carbonyl carbon present in the system. Let us suppose the first carbonyl carbon is C14 and second carbonyl carbon is C12. Now point is, on which carbonyl carbon this OH minus will attack. So as it is electron rich, it will try to attack on that carbonyl carbon which has more deficiency of electron. And if we compare C14 and C12, what we can see, on C14 we have a benzene ring that is increasing the electron density by plus m, and on C12 we are having benzene ring with OCH3, and both of them are having plus m. So this part of the molecule will have more plus m as compared to this part. And if this is having more plus m, so there will be more electron density on C12 as compared to electron density on C14. And if C14 is electron deficient, so OH minus will attack first on C14. If OH minus is attacking on C14, what will happen? The electron will shift to oxygen. In the second step, electron will come back, and this complete group will depart from here, and it will attack on the other carbonyl carbon, and electron will be shifted to oxygen. So the product which we will get, that will look something like this. C double bond O, 14. Over here we'll have OH, then C will have O minus. One side will have benzene with OCH3, and second side will have benzene. And after this O minus, this O minus will take away the H plus from the substrate, or H plus, this acidic hydrogen. So this will be converted to this molecule, C double bond O, O minus, 14, C, this is C12, C12 is connected with OH, and it is connected with two benzene, one benzene ring and another a benzene with OCH3. So this is the product of this reaction. Let's do one more question on this benzylic acid rearrangement only. Let us suppose we are having a compound like this. Let us suppose we have a substrate like this, and this substrate is treated with NaOH. So OH minus, again it is electron rich. Generally you can guess benzylic acid rearrangement as those compounds which are having alpha keto groups. Those which are having alpha keto group, they generally shows benzylic acid rearrangement. So OH minus will attack on this carbonyl carbon. The pi electron will shift to oxygen. In the next step, electron will come back, and this bond will break, and it will shift to oxygen. So the product which will be formed, I am writing the product in this case, the product which will be formed, that will look something like this. I hope it's clear. And this negative charge which is formed, that will attack on the carbonyl carbon, and electron will be shifted to oxygen. So there will be formation of a 5-member ring. We can number the carbons as 1, 2, 3, 4, 5. There is a bond between first and fifth carbon, so you can draw it like this. A 5-member ring will be formed. This is first, second, third, fourth, fifth. On the first carbon we'll have O negative, and on the first carbon only we have C double bond O and OH. Now O minus will take away the H plus, the same reaction. So the product will be this. It will be OH, and this side will have C double bond O, O minus and Na plus. So this reaction is known as benzylic acid rearrangement. So till now we have discussed two rearrangement reaction. The first was Beckmann rearrangement, and the second one was benzylic acid rearrangement. After this, the third reaction which I am going to discuss today is Knoevenagel reaction. Knoevenagel. Knoevenagel reaction. You can write about this reaction. This reaction is condensation of, I'm writing condensation of aldehydes, and ketones with compounds, condensation of aldehydes and ketones with compounds having active methylene group, in presence of basic catalyst, to form alpha beta unsaturated compound is known as Knoevenagel reaction. The basic catalyst which we are using in this reaction, the basic catalyst may be ammonia or its derivative. The basic catalyst of this reaction will be ammonia or its derivative. Now let's try to understand the mechanism of this reaction. So let us suppose we are having a carbonyl compound. So let us suppose we are having RC double bond O and R, and this is treated with a compound which is having active methylene group. So I am writing it as CH2COOR whole twice, and it is in presence of a base which is ammonia or ammonia derivative. So I have taken it as R3N. So what will be product of this reaction? So the product of this reaction is RCR double bond CH and COOH. This is the product of this reaction. Now how we are getting this product, that we have to understand. So in the first step, before that, you just try to check the structure of this molecule. So it is CH2, C double bond O, OR, and this side again C double bond O, OR. Now initially what is happening, R3N, which is a base, is treated with CH2, COOR whole twice. So we can see that this hydrogen, which is present, that is acidic hydrogen, and R3N which we are using, that is a base. So base will take away the acidic hydrogen and it will be converted to R3NH positive charge plus CH negative charge with COOR whole twice. And this carbon with negative charge, that will behave as nucleophile in this reaction, and it will attack on the carbonyl carbon. This carbon with negative charge will attack on this carbonyl carbon, and electron will be shifted to oxygen. So the product which will be formed, that will look something like this. O minus, this is R, then over here we'll having CH, then COOR whole twice. I hope this still here it's clear. Now after this, what happens, this O minus takes away the H plus from this R3NH which is formed in the above step. So this will be converted to RCOH, RCH and COOR whole twice. After this, what will happen? So after this, we have studied in aldol condensation that if this is heated, there will be loss of H2O, and that will be converted to RC, R double bond C and COOR whole twice. Now this H2 which is coming out, it will react with this compound, and what we know that if an ester is treated with water, that will be converted to carboxylic acid. So the compound which will be formed, That will be RCR, double bond C with COOH and COOH. And this also we know that if two COOH are present on the same carbon, so there will be loss of CO2 molecules. It will form RCR, double bond C and COOH on one carbon and H will be on the other carbon. So this is the product. This is the final product of Knoevenagel reaction. So today we have done 3 reactions. The first one was Wittig rearrangement, second one was benzylic acid rearrangement, and the third one is Knoevenagel reactions. Thank you. That will be for today.